now the third part of simple harmonic motion, I just want to summarize all the important equations we have learned so far in simple harmonic motion. So in this chapter, these are the most important formulas we are going to use. Okay, first is the displacement time equation, which is x equal to a sine omega t. Okay, a sine omega t, and then we have velocity time equation, v equal to a omega cos omega t, and then we have acceleration time equation, a equal to negative a omega square sine omega t. Okay, displacement time, velocity time, acceleration time. Okay, one thing, yeah, you see here, in this chapter, we owe this omega t, you know omega is, omega actually is always, omega is called angular velocity or angular frequency. Yeah. When you talk about angular velocity or angular frequency, they are the same thing. They are referred to omega. But normally angular velocity we use radian per second. Angular frequency we just use per second, because the radian unit sometimes can be ignored. Sometimes we don't write the radian because it's not part of SI unit. Sometimes we just write per second. Okay. When frequency, normally we just write per second. Angular frequency, yeah. Angular frequency is not the same as frequency. Frequency is frequency. Angular frequency is omega. Okay. Now, one thing is the omega is 2 pi f or 2 pi over period, isn't it? So when we talk about pi, it is referred to the radian, isn't it? Radian. So this omega has pi, has radian. So in this chapter, in actually our simple harmonic motion and later on the chapter called the mechanical wave and sound wave, we all use radian. Remember, don't use degree. Don't use degree in this chapter. You must change your calculator to radian. Okay, radian. If not, you get the wrong answer. If you use degree, you get the wrong answer. So make sure you change your calculator to radian before you even start the chapter. Before you even start the chapter, you change your calculator to radian. Okay? Because we are using omega, which has pi, which is radian. Now, okay. After besides that, I want you to notice here. In front of here we have A. This one is actually the maximum displacement amplitude, and in front of here we have A omega. Actually, this is the maximum velocity. A omega, and here we have A omega square, which is the maximum acceleration. Okay, A omega square. This is the maximum value of displacement, velocity, and acceleration. Okay, but when we talk about maximum acceleration, the negative sign we ignore. No need to put the negative sign. Okay, when we want to find the maximum acceleration, we just want the magnitude. No need the negative sign. Okay, you just put A omega square. Okay, sometimes the question will come out with sine. Sometimes the question will give cos omega t. Then you need to apply how to get the velocity and acceleration equation if it is cos omega t for displacement. That one you have to use your mathematics knowledge, how to differentiate. Differentiation is very important. Differentiate knowledge is very important in this chapter. Okay, so you need to know how to differentiate them. I will show you several examples how to differentiate. Okay, don't worry. So after that, displacement time, velocity time, acceleration time, we also have velocity displacement, which is v equal to plus minus omega square root a square minus x square, v versus x. And we also have acceleration versus displacement equation, which is a equal to negative omega square x. This is the most important equation in simple harmonic motion, because it explains what is actually simple harmonic motion. Simple harmonic motion is actually the acceleration of the object is proportional to the displacement of the object. That means actually, if you look at the spring mass system, look back to the spring mass system, the more we can say, the more the spring, the more the x, we talk about x, the more the string the more the spring expand, so the stronger restoring force, the spring will pull back with stronger force. That's what I mean by acceleration. The higher the x, the higher the acceleration. The higher the spring expand, the higher the spring pulls back, the restoring force. The higher the expansion, the higher the restoring force. The higher the expansion, the higher the force in the spring to pull back the object to the equilibrium. Okay? That's called simple harmonic motion. Secondly is acceleration is opposite direction with displacement. That means when you expand, when you extend the string, the spring pulls back in the other direction, in the opposite direction. You expand the spring in positive direction. Okay, you expand the spring in positive direction. The spring pulls back in the opposite direction. So the expansion of the spring is x. The spring pulls back is the acceleration. Spring pulls back, acceleration, because it's the force, restoring force. F equal to ma. Force is related to acceleration. Okay? Good. This is simple harmonic motion. So after that, we talk about the energy. We have potential energy versus displacement. We have kinetic energy versus displacement, and we also have the total energy versus displacement, which is U equal to half kx square. This is the force. This is the potential energy stored in the spring, which is also half m omega square x square. Yeah, the higher the x, the higher the U. Okay. The kinetic energy versus displacement is this half kx square is the spring. Okay, this one happens in the half kx square happens in the elastic energy in the spring, and half mv square is the block, which is oscillating. Okay, half mv square oscillating, which is half m omega square a square minus x square. And both of their maximum value is equal to the total energy, which is equal to half m omega square a square. Okay? So that's all about the energy. Total energy is U plus K. Now the simple pendulum. These two formula are very important. Simple pendulum is period equal to, want to find the period of the pendulum. The period of the pendulum depends on the length of the pendulum and also the gravitational acceleration of the Earth or any planet. Okay, the gravity of the planet and also the length of the pendulum. It does not depend on the mass of the pendulum. The mass of the pendulum is not a factor to determine the period of the pendulum. Yeah, mass does not affect. The bigger the pendulum, the period is the same. The mass does not affect the period or even the frequency. Actually, this period is actually 1 over frequency, isn't it? So period is you can change period to 1 over frequency. So the mass does not change, the period does not change the frequency. Okay, about the spring mass system, no matter it's horizontal or vertical, to find the period of the spring mass system, for these two, we still use the same formula. Yeah, horizontal or vertical, still the same formula. Period equal to 2 pi square root m over k. So the period of the spring mass system depends on the mass. This one, it depends on the mass. not like the pendulum. The spring mass system depends on the mass. The bigger the mass, the longer the period. Yeah, slower to oscillate. Also depend on the spring constant. The higher the spring constant means the harder the spring, the shorter the period. It oscillates faster. The shorter the period, it oscillates faster. So, and this formula can derive the formula. If you do by yourself, after that, you apply the period omega equal to 2 pi over period. You apply this formula into here, you will get this formula. You do yourself, trust me. You will get K equal to M omega square. We have M and K here. Omega is 2 pi over this period. So you get from this formula, period equal to 2 pi square root M over K, you get K equal to M omega square. So these two formula is the same. It's the same. K equal to M omega square is the same as this period formula. Okay? Good. Next is the graphs. I want to talk about the graphs. Okay, so remember we have this formula. You need to identify which formula to use. So all this formula is very important. You must know how to know when to use which formula. If you give the question give you time, ask you to find displacement, use xt equation. The question give you time, want to find velocity, you use vt formula. If the question give you displacement, it asks to find velocity, you use velocity displacement equation, and don't use velocity time equation. Okay, depend on the formula. Depend on the questions. Okay, about the graphs. Talking about the graphs, we have displacement time equation, displacement time graph, velocity time graph, and acceleration time graph. All these just depend on the formula. The displacement formula is A sine omega t. So it is a sine graph. We draw a sine graph. Okay, sine graph. And the maximum here is what? Look at here. A omega square. See that? So this is for x is a sine graph. So it is the maximum is A. So you put A. The velocity graph is a cos graph. So you draw a cos. And the maximum is A omega. So A omega at top and bottom. A omega negative A omega. For acceleration time graph is a negative sine graph. Negative sine graph. So it's a inverted sine. Yes, sine is like this. So negative sine is invert the sine. Invert the sine. Negative sine graph. And maximum is A omega square. So you put A omega square. Okay. A omega. Velocity is A omega. Acceleration is A omega square. That's the maximum value. You know that? This is the max. This is the maximum displacement. This is the maximum velocity. This is the maximum acceleration. Okay. And don't forget to complete one wave is period. One period. This one also one wave period. This one also one wave period. Remember the period. Period is the time to complete one oscillation. Time to complete one oscillation. Okay. Then we have energy versus displacement graph. See that? Energy versus displacement graph. Using this equation, kinetic energy versus displacement, potential energy versus displacement, and total energy versus displacement. So, total energy versus displacement. So we have equilibrium 0, x equal to 0, x equal to amplitude. We have positive amplitude and negative amplitude. The total energy is a straight line because it's always constant, half m omega square a square. So the total energy is actually half m omega square a square. That's why here, this value is, here we need to label half m omega square a square. We need to, this part is half m omega square a square. This part is displacement. So it's amplitude. Okay? And then the red line, this red line is potential energy, the energy in the spring. Okay, energy in the spring. So at equilibrium, no energy stored in the spring because no expansion, no compression. But an amplitude, positive amplitude means maximum expansion has a maximum elastic potential energy. Maximum compression is negative amplitude compression, also has maximum elastic potential energy. Okay, so you see, when at maximum, when at here, you see that. So at U max, it is equal to E total. U max also equal to E total. You see, it touched the graph touched the ET. But for the kinetic energy, the maximum is at the equilibrium. Kinetic energy maximum at equilibrium. Yeah, because why? The block. We talk about potential energy. It is the spring. When we talk about kinetic energy, we talk about the block. So you see that the block is fastest at the center at the equilibrium, because all the spring energy convert to the kinetic energy of the block. Here at the center, the K max is equal to total energy. It touch the E total. Yeah. So total energy, the K max is equal to half m omega square a square at this point. So but the amplitude, at the amplitude, kinetic energy is 0 because velocity is 0. Okay. So that's all. Remember to label the A omega square, period, and remember to remember the label the amplitude, display the energy versus displacement, amplitude for this for here x axis, and for the y axis remember to label the half m omega square a square for energy. Okay, so that's all for our summary in simple harmonic motion. So I'm going to discuss several questions in this chapter with you, so stay tuned for the upcoming videos. Bye.